Hi, my name is Zhihao, and I'm a PhD student at Stanford working with Matej Zaharia and Alex Aiken. So today I would like to talk about one of our recent work on optimizing DNN computations by using relaxed graph substitutions. Today's DNN computation graphs are becoming increasingly more complex and diverse, so different operators and different graph structures has been proposed for different learning tasks. So from a system perspective, this actually brings a very interesting research problem. So how can we systematically optimize DNN computation graphs on today's modern hardware platforms? So existing framework have been using heuristic approaches to optimize DNN computation graphs. So they perform a number of graph transformations that are manually designed by domain experts to optimize the performance of a DNN computation graph. For example, commonly used operator fusion could be fusing a convolution and a ReLU into a single convolution plus ReLU operator, because we know heuristically this fused operator will be faster than performing the two operators separately. And applying this graph transformation is very simple. Because these graph transformations are designed to optimize your performance, so you can directly apply them whenever possible on your input graph, and this will give you an optimized graph in existing frameworks. So we found there are actually several limitations with this heuristic approach. The first is robustness, because these graph transformations are designed based on experts' heuristics on common graph and architectures, so they may not apply to all models and hardwares. So as a result, you can find people on GitHub or Stack Overflow complaining that if I use XLA, which is TensorFlow's graph optimizer, why my graph is slower instead of faster than without using any graph optimization. So the second limitation is scalability, because today's DNN model keeps introducing new operators and also new graph structures to achieve new model accuracy. But so these all require a significant amount of new graph transformations to optimize these new operators and new graph structures. So the third limitation is performance issue, because existing graph transformations are designed for common graph structures, so they may miss some subtle optimizations for specific graphs. So let me show you the example of a missing optimization in existing framework. So this figure is the optimized computation graph by existing framework. And so I will show you one missing optimization, and of course we found that in this paper. So maybe I should stop for a few seconds to let you think if you can transform this graph, if you can manually transform this graph to a more optimized form. So this is a non-trivial optimization, so I will just tell you the answer. So consider we have this 1-by-1 convolution, right? We can just change it to a 3-by-3 convolution by enlarging the convolution kernel. So this is possible because you can just set the extra weights to 0, so that mathematically the 3-by-3 convolution will compute the same result as this 1-by-1 convolution, right? So after that, you can fuse these two 3-by-3 convolution by concatenating the output channels of the two 3-by-3 convolution. So this is an optimization because on the new graph, you only have to access the input tensor once, compared to the original graph where you have to access the input tensor twice. And finally, you can also fuse the convolution and the following addition and ReLU to a single convolution plus ReLU operator. So we found that this final graph is 1.3 times faster on V100 GPU, but 10% slower on KH GPUs. So maybe I should do a test. So how many of you can manually figure out this optimization by looking at the input graph? It's very hard, right? So, and also, this is a non-trivial optimization because it does not constantly improve performance. It only makes your performance better on particular hardware. So this also indicates that when we are trying to design our graph optimizations, we really need to consider the exact hardware we are trying to run our graph on. So let me show you how we can automatically find this optimization. So we propose a search-based approach. So first, instead of just considering graph transformations that optimize your performance, we consider arbitrary graph optimization, graph substitutions, as long as it preserves your computation. And second, we define a search algorithm to explore the space of potential computation graphs. And combining these two techniques, we can find optimized DNN computation graphs. So we implement this idea in a system we call MetaFlow. So this slide shows an overview of MetaFlow. So we take as input an computation graph and also a list of potential graph substitutions. So MetaFlow, a search-based graph optimizer, will automatically explore the space of all candidate graphs that are generated by different combination of your graph substitutions. So all candidate graphs in this space are equivalent, so they can compute the same output, but they have very different runtime performance. So the graph optimizer will explore that search space and generate an optimized computation graph. So we found there are two challenges in exploring the search space of candidate graphs. One is that we have many graph substitutions are irreversible. For example, you can change a 1-by-1 convolution to a 3-by-3 convolution, but you cannot change it back, right? That means if you apply some substitution and get a new graph, you may never get back to the original graph by performing other substitutions. So to solve this problem, we propose a cost-based backtracking search so that we can backtrack our search path and be able to reverse and undo some substitutions whenever possible. And the second challenge is that for today's deep neural networks, the search space is too large to directly search for. So our solution is we propose a flow-based graph splitting algorithm to partition the large graphs to multiple small subgraphs. So the bottom figure shows a data flow of our approach. So for any arbitrary input computation graph, we first perform a flow-based graph splitting to split the original graph into multiple individual subgraphs. Then we can concurrently run our search algorithm on different subgraphs and get optimized subgraphs. And we can construct an optimal computation graph by using the optimized subgraph as basic building blocks. So first, let me show you our flow-based recursive graph splitting algorithm. The problem here is that even very good search algorithms are too expensive for large graphs. So we need a way to break your entire graph to small subgraphs. So when we are trying to break it into subgraphs, our goal is to minimize the lost substitutions. We would like to preserve as many substitutions as possible. So we formulate this problem to a max-flow min-cut problem. So we define the capacity of each operator to be the number of substitutions that will use this operator. For example, this is an input computation graph, and each color shows a different substitution. And you can count the number of substitutions that will be disabled if we split along this operator. And in this case, you can find, in this case, the min cut of the graph will give you a natural splitting point to split a original graph to subgraphs. And we can recursively run this graph splitting algorithm to partition a large graph to smaller graphs with reasonable sizes. So once we have individual subgraphs, our next task is to optimize different subgraphs. So we use a cost-based backtracking search. So in our cost model, it estimates the cost of the original computation graph as the summation of individual operator costs. And we measure the cost of each distinct operator by running them on hardware. So this measurement is very similar to our FlexFlow work I presented yesterday. So we decided to use backtracking search to explore irreversible substitutions. And so we can concurrently perform our cost-based backtracking search on subgraphs, and this will give us optimized subgraphs. And after that, we can perform a second round of backtracking search along the boundary between different subgraphs to see if we can further optimize the boundary. And after the second round of the optimization, we can get an end-to-end computation graph. Okay. All right. So we have evaluated compare our idea with several existing baselines. One is TensorFlow, the second is TensorFlow XLA, and the third one is TensorRT. So these are existing DNN graph optimizers for GPU. And we consider 5 DNN benchmarks, 3 for image classifications and 2 for language tasks. And so this table shows a statistic of our graph substitutions. So we consider 8 performance decreasing substitutions. So we consider substitutions that will temporarily decrease your runtime performance, but will transform your graph to a new format. And we also consider operator fusions that has been widely used in existing frameworks. And third, we also consider some algebraic identity transformations, such as we think A plus B is equal to B plus A, and A times B is equal to B times A. So we can also consider these substitutions. So in total, 22 substitutions are considered in our evaluation. And because MetaFlow is pluggable, so you can also add future substitutions into our search engine. So the first question I would like to answer in our evaluation is, can MetaFlow improve end-to-end performance? So we compare MetaFlow with the best among the existing baseline, and this table shows the relative speedup. So we can achieve 1.1 to 1.6 times speedup compared to the best existing baseline. And one thing I would like to point out is that our improvement is achieved without any loss of model accuracy because we preserve computation. So you can almost achieve this optimization almost for free because you didn't have to worry about your accuracy loss at all. So we think this is a very nice property of MetaFlow. And the second question in our evaluation is, can MetaFlow be used within other frameworks beyond our MetaFlow own runtime? So to validate this, we run the original graph and MetaFlow optimized graph on TensorRT runtime and see if our optimized graph is faster than the original input graph on TensorRT. So this table shows the relative speedup. And as you can see that our MetaFlow optimized graph is also faster than the original graph, even on TensorFlow, even on TensorRT engine. And this also indicates that our graph optimizations are general and can also be applied to other frameworks. And our next task problem in evaluation is training. Can MetaFlow also be used to improve training? Because previously we have shown that it works for inference. So in MetaFlow, training and inference are defined as just as different computation graphs. So the bottom figure shows an example inference graph and this corresponding training graph. The difference is that, so you can see that there are more data dependencies in the training graph. And MetaFlow can use the same pipeline to optimize both graphs. So this table shows our training performance comparison. So we run the original graph and MetaFlow's optimized graph on TensorFlow engine. And we observe 1.1 to 1.2 times speedup on different data sets. And we also observe that our speedup on training is smaller than our speedup for inference. And this is because for training, there are the additional data dependencies for training will limits the substitutions that can be applied. So as a result, we only achieve smaller speedup for training. And we also found that MetaFlow can automatically find a different optimized graph on different hardware. So the left figure shows an inception modular, and the right figure shows the corresponding optimized graph for V100 GPU and K80 GPU. And the shadowed rectangle highlights the graph optimizations that are performed on different GPUs. And as you can see that different optimizations are performed on different GPUs. This also means that you really need to consider what hardware you're trying to use when you are doing graph optimizations. So for future work, we are actively working on MetaFlow. And one of our future work is to support automated substitution generation. So this table figure shows existing overview of MetaFlow. So we rely on users to define potential graph substitutions and try to search how to optimize by using existing substitutions. And our future work is to design an automatic substitution generator that will look at the input computation graph, analyze the operators and structures in the input computation graph, and automatically generating cross-bounding graph substitutions. And this will be also fit to our search-based graph optimizer. So to conclude, I have presented a search-based approach to automatically optimize DNN computation graphs. And we show that our approach is able to outperform state-of-the-art approach by up to 1.6 times. And all our code is available online. And feel free to use it to optimize your own graph on your hardware. Thank you.
Thank you. Questions?
Yeah, Minsik provided very interesting work. So,
thank you.
Do you have any runtime information on like DZ graph optimization?
What do you mean by runtime information?
I mean, you need to spend time to transform the graph, right?
Right.
So can you comment on, let's say, then how long it would take, let's say, that for resident 50, and then let's say that how long would it take without any graph partitioning?
Oh, right. So we have some numbers in our paper. So if we didn't do any graph partitioning, directly train on the original graph, then it may take hours, even for some small graph with only 20 or 30 operators. The end-to-end search will take hours or even days.
Okay.
So that's why it's too large to directly search. So we need some way to partition the graph.
But have you compared your quality without any of those, let's say, the graph partitioning? I mean, did you see any, let's say, the difference in terms of quality with and without partitioning approaches?
Right. So we measure on some small graphs that we can exhaustively enumerate all potential subgraphs, and we are able to find the same optimized graph with and without graph partitioning.
All right, thank you.
Thank you.
This is Lin Yuan from Amazon. So in your talk, nice work, first of all. So in your talk, in your search strategy, basically you search mapping the graph into a different combination of nodes. Have you explored the dimension of mapping the nodes to different hardware? For example, running certain nodes on certain hardware and then the rest of the nodes on GPU or CPU or something like that?
Yeah, this is a very interesting question. So the question is, have we tried to map graph onto different hardwares? So we haven't tried that, but that would be a very interesting future work direction. And I think that would be because different operators have different preference in terms of hardware. So GPU is good at something, CPU is good at some other thing, and FPGA is, I mean, each accelerator has its advantages. So it's interesting to explore the space of how to combine the advantage of different hardware accelerators.
Thank you.
Thank you.
Hi, I'm Takeo Imai from NII in Japan. My question is that I wonder how to give the cost or cost model in your. I might miss your words, but I don't understand.
All right. So we assume that the cost of the graph is the summation of cost of individual operators. So we just sum the cost of individual operators to estimate the cost of the graph. And we we measure the cost of individual operators by measuring the operator on hardware. So we directly run them on hardware to know the cost of the operator.
So the cost, is the cost depend on the hardware?
Yes, the cost depends on hardware.
So how to estimate that?
So we directly run them on hardware.
Okay.
Yeah, maybe you can talk offline. Maybe.
I see.
Thank you.
Okay, thank you.
Hi, I'm Yao from Amazon, and I have a question about MetaFlow itself. You mentioned that you have its own runtime or execution engine for MetaFlow.
Yes.
So the number you said that here is up to 1.6 is comparing directly like using MetaFlow execution engine with TensorFlow execution engine, or it's just like optimize the graph, and you use TensorFlow execution engine to run it and achieve 1.6.
Right. So actually, in the paper, we show numbers for both executions. So we run the optimized graph on our runtime and also on other runtimes. We show all the numbers in the paper. But for this particular figure, the speedup is the comparison is between the original graph in best existing framework and the optimized graph in our MetaFlow framework.
Okay. So is it possible that some performance gain comes from the difference of the execution engine,
right,
instead of?
So we found, because we directly use Cudean library and Kubelet library, so as a result, our MetaFlow and runtime has almost identical performance as TensorRT.
Okay.
Right.
Okay. Thank you.
Thank you.
By the way, Zhihao was participating in artifact evaluation. It was really cool to try your tool. Thank you. Okay, let's thank the speaker.